All right, my friends, before we talk about how to, write this out and explain yourself and all that stuff, so I wonder how many of you guys kind of looked at this rule and you're like, I feel like this, the way they're defining the terms would be so much less complicated if that +1 wasn't there. And if that didn't occur to you, then maybe just take a minute and like kind of imagine that +1 like wasn't there. Well, the fraction, the way the terms would be defined would basically have been 1 over n times the square root of n squared, which would have been 1 over n squared, which totally would have been a p series. And those are the easiest things ever to figure out if they converge or diverge, because you just look at the value of p. Anyway, so, and it's that kind of situation that where there's just a little piece that you wish wasn't there. That's when the comparison test is really going to be kind of like the tool for the job. Okay, so let's come over here and talk about just the comparison test in general, and then we can go back and show how you could use a comparison test argument for that warm-up problem. Okay, and keep in mind as you go through chapter 8, the most important part for you to learn is how to argue, essentially, or how to justify your position using the theory that we're learning. And so this lesson is dedicated to how to write out a comparison test argument, when to use it, when to not use it, stuff like that. Okay, so I like explaining the comparison test with a little picture where you're just showing like what the terms would look like if you graphed them. And so instead of an x-axis, you'd have an n-axis, so first term, second term, third term, fourth term, fifth term, sixth term, seventh term, eighth term, ninth term. Actually, you know what would be probably a good idea would be for us to like, do you remember like this notation? Remember that? Showing that like the axis got kind of scrumpled up, and so you're going to make a big jump in values. So kind of put one of those jiggity jaggities. Anyway, so we'll do 1, 2, 3, 4, 5, 6, I guess 7. And then out here, let's say you're at, 290, and then this would be 291. I don't know, like way out there. Okay. So what we're going to do is we're going to compare two sequences essentially. And so we're just talking about the terms of the sequence. So let's say you have a sequence and it's like called a sub n. Okay. And so let's say a sub 1 is like here. A sub 2 is here, so let's label them. A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, A sub 6, A sub 7, etc. We'll put A sub 290, so 290th term, and 291st term. So there we go. These are the A's. Okay, and then let's have the B's, and I think what I'll do is just change the color here for the B's to make it so I don't have to label everything, because it gets kind of full pretty quick. So let's see, green's good. Okay, so the B's, we're going to have all the B's be above the A's. And the truth is it doesn't have to start out that way. Like you could totally have, at first you could have some backwards, but we'll just kind of keep it. So let's say the B's are always above the A's. B sub 7, B sub 8, or sorry, B sub 290, B sub 291. Okay, so the idea here behind the comparison test is if you have a setup like what I'm describing here. So if you have, first of all like the terms are positive, or at least what's called eventually positive. So all the term values are above 0, and then you have the A sub n's are always less than the B sub n's. If you have that line up, then let's kind of think about this. So if the sum as n goes from 1 to infinity of a sub n. Let's say you know that that diverges. Then what would you know about the sum as n goes from 1 to infinity of b sub n? So go ahead and fill in the blank there with what you think. And if the sum as n goes from 1 to infinity of all the b sub n's, if that converges, then what would you know about the sum as n goes from 1 to infinity of all the a sub n's? Okay, so go ahead and think about how you would finish these statements. So if we know that when you add up all the a sub n's, you get something that basically adds up to infinity, then I hope it makes sense that since all the b terms were bigger than the a terms, they would definitely add up to infinity also. And so we would fill in the first blank with the word diverges or also diverges. And if you, however, if you knew that the sum as n goes from 1 to infinity of all the b sub n's, if you knew that that added up to something finite, and since all the a terms are less than that, then I hope it makes sense that if all the b's add up to something finite, then all the terms that are less would also add up to something finite. And so there we go. Okay, and this, my friends, is the comparison test. That's the theory for this part. Now, I hope it makes sense that if in a situation like this, where the a sub n's are less than the b sub n's, if you know that the sum of all the a sub n's converge, that wouldn't mean anything about the b sub n's. And similarly, if the sum of all the b sub n's, if they diverge, then it wouldn't mean anything about the sum of all the a sub n's. So the position for the terms really matters. That's an important part for the comparison test. So watch out for that. So which one's higher, which one's lower? And does the theory make sense? So for for this warm up here, the way that you could show a comparison test argument would look like this when you try to write it out. Okay, so first off to the side, let's kind of think about, well, what would we compare it to? And let's just kind of make sure we've got the right positioning, okay? So we're going to think about, like, wouldn't it be nice if that +1 wasn't there, right? So, okay, so we're going to see if we can compare it to the sum as n goes from 2 to infinity. This is just scratch work, so you could just watch this part if you want. And then that would be the sum as n goes from 2 to infinity of 1 over n squared. Okay, well, what do we know about that? That converges, right? So now what we need to do is make sure that we've got the right positioning. So if this one converges, that means that the terms add up to something finite. So we'd be arguing that this one that we're given, we'd be arguing that that one also converges. But in order for the logic to work, we would have to show that if these are the 1 over n squareds, where would we need these to be located in order to say that if all the 1 over n squareds add up to something finite, that these do too? Oops. That's right. We would need them to be, we'd need those terms to be underneath, you know? And so are they, you know, are the 1 over n times square root of n squared plus 1, is that always going to be less than 1 over n squared? So let's think this out. This one on the left, you're dividing by a bigger number. So what happens if you divide 1 by a bigger number? If you divide something by a bigger number, you do get something less. And so that means, yes, we do have the positioning that we need, and we can absolutely use the comparison test argument here. And so here's what it looks like when you write it out. So we're going to say compare to, and then I always show this in 2 steps. So I show really clearly that all I'm doing is getting rid of the +1, first of all, and then I simplify it. And so first thing you do is say what you're comparing it to. And then the next thing that you do is you basically use previous knowledge to say what this simpler sum does. And this simpler sum just happens to be a p-series with a p-value of 2. And so we would say that this is a convergent p-series. Since the p-value was 2. So first thing, say what you're going to compare it to, make it really clear, and then use previous knowledge to argue whether that one converges or diverges. Next step, state your positioning. So of the terms, okay? So we're not comparing the sum at this point, we're comparing just the terms, the value of the terms, which one's higher, which one's lower, okay? So we could say, use some fun transitional word. I like furthermore. How about furthermore? We would say that 1 over n times the square root of n squared plus 1, how would that compare to 1 over n squared? Since after all we did was take off the plus 1. So I hope it makes sense. We're dividing by a bigger number, so we'd end up with something less. So all the terms are underneath the terms of the one where we've already figured out converges. Therefore, we could conclude that the sum as n goes from 2 to infinity of 1 over n times the square root of n squared plus 1 also converges by the comparison test. All right, and to my fellow math jocks out there, yes, you need to write the words. It's probably the most important thing you can do for getting ready for questions like this on the AP exam, because they are going to want you to show knowledge of the theory, and you'll have to have certain little phrases practiced and in your back pocket to feel like you really know how to maneuver through the questions that they'll ask you. Okay, so let's go ahead and see how you'll do with example 1. Determine the convergence or divergence of each series. In this case, let's start with the sum as n goes from 1 to infinity of 5 over the square root of n cubed plus 2n. All right, see how it goes. Check in with me in the next video.